Now we shall move on to the change of states of matter. On the left, you see an image of ice, a solid form of water. At low temperatures, water molecules are tightly packed in a structured, orderly arrangement, forming ice. As we apply heat and increase temperature, the molecules begin to move more freely, transitioning the solid ice into a liquid state, water. If we continue heating, the water will eventually become a gas, steam. This entire process is known as a change of state. On the right side of the slide, you see a phase diagram that maps these transitions. Along the y-axis, we have pressure, while the x-axis represents temperature. The diagram shows the relationship between pressure and temperature as water moves between solid, liquid, and gas states. The green curve represents the transition from solid to liquid known as melting. The blue curve shows the transition from liquid to gas known as vaporization. Notice the triple point where solid, liquid, and gas can coexist at specific conditions of temperature and pressure. At very high temperatures and pressures, we reach the critical point where the distinctions between liquid and gas phases disappears, leading to a supercritical fluid. This diagram highlights how matter behaves under different temperature and pressure conditions, helping engineers understand the physics behind phase changes in materials like water. When a solid is heated, its particles gain energy and vibrate more vigorously. At a certain point, known as the melting point, the particles gain enough energy to break away from their fixed positions, and the solid transitions into a liquid. Similarly, when a liquid is heated to its boiling point, the particles gain enough energy to overcome their forces of attraction and escape into the gas phase. In this slide, we are looking at two key phase changes, melting and boiling. First, let's talk about melting. When a solid is heated, its particles gain energy and start vibrating more vigorously. This causes the solid to expand. At the melting point, these vibrations become so intense that the particles break free from their fixed positions and the solid turns into a liquid. Next, we have boiling. When a liquid is heated, its particles gain energy and move around faster. This increased movement causes the liquid to expand. At the boiling point, the particles have enough energy to overcome the forces holding them together, and the liquid changes into a gas. When gases lose heat, their particles slow down, allowing them to come closer together and condense into a liquid. Likewise, when a liquid is cooled, its particles lose energy and eventually become fixed in place, forming a solid. This process is known as freezing. In this slide, we explore the relationship between temperature and kinetic energy. The temperature of a body is directly related to the average kinetic energy of the particles within it. In simple terms, the more kinetic energy the particles have, the higher the temperature of the body. For example, if liquid A has a higher temperature than liquid B, it means that, on average, the particles in liquid A have more kinetic energy than those in liquid B. This concept is fundamental in understanding how temperature reflects the movement and energy of particles in different states of matter. Evaporation occurs when a liquid below its boiling point changes into gas. This happens when some particles in the liquid are more energetic than others, and they are often found near the surface of the liquid. These energetic particles have enough energy to overcome the forces holding them in the liquid. As they escape into the air, they turn into vapor. The less energetic particles, which remain in the liquid, continue to move more slowly. Evaporation plays a key role in various natural and industrial processes, and it occurs continuously, even at temperatures below boiling point. Several factors can affect the rate of evaporation, including temperature, surface area, wind, and humidity. For example, higher temperatures and larger surface areas speed up evaporation, while higher humidity slows it down. This slide explains the cooling effect of evaporation. Evaporation causes cooling because when the high-energy, fast-moving particles escape from a liquid, the remaining particles are slower and less energetic. As a result, the temperature of the liquid decreases and the liquid cools down. This principle explains why we feel cooler when we sweat. As the water droplets on our skin evaporate, they absorb heat from our body, making us feel cool. This natural process helps the human body regulate and maintain a constant temperature. Evaporation is an important mechanism that ensures our body stays cool, especially in hot conditions, preventing overheating and maintaining constant body temperature. This slide compares boiling and evaporation, two processes that involve the transition of a liquid to a gas. Even though both processes result in the same change of state, they are fundamentally different. Boiling occurs at a fixed temperature, the boiling point, and is a fast process. It happens throughout the entire liquid, and you can observe bubbling as the liquid turns into gas. On the other hand, evaporation can occur at any temperature, including below the boiling point, and it is a slow process. Unlike boiling, evaporation only occurs at the surface of the liquid, and there is no bubbling involved.